If you've ever looked at a massive utility-scale battery farm and wondered how on earth engineers decide exactly how many batteries and cables they actually need, well, you are in the perfect place. We're going to dive right into it. The biggest thing you need to know up front, unlike a backup battery you might have at your house, a utility-scale battery is designed to support the wider electrical grid first, and absolutely everything else is a distant second. To really grasp the sheer scale we're dealing with today, let's look at this number. 8,460 kilowatt hours. That is our total raw power load demand for the site. Now, it's super tempting to think this number is our anchor. In a normal residential off-grid setup, engineers map out exactly how much energy a house consumes before they ever order a single solar panel. But for a utility-scale design, that's actually a massive misconception. The engineering workflow here absolutely does not begin with the local load demand. So here is our roadmap for today. Calculating the power demand, sizing the core equipment, engineering the cables, and finally, why the grid always wins. All right, let's jump straight into section 1, calculating the power demand. Now, a traditional engineering workflow usually moves pretty logically. You calculate your specific local loads, you size the solar system to capture the energy, you size your battery energy storage system, the BESS, to hold it, and then you engineer the cables. Makes total sense, right? Well, utility-scale projects flip this entire sequence on its head. The battery is sized specifically to support the grid. Local requirements, like heavy-duty EV chargers or temporary construction equipment, literally just piggyback off whatever capacity is left over. When we do break down those localized site demands, we might see a split like 3,930 kilowatt hours during the morning peak and another 4,530 kilowatt hours at night. This is roughly 2.43 megawatt hours per day specifically for things like on-site EV charging and some construction power. But here's the catch. This day and night split is purely a secondary operational service. The system's energy management brain will simply schedule this local charging whenever there's surplus solar generation, carefully ensuring it never ever disrupts the battery's primary mission for the grid.
Moving right along to section 2, sizing the core equipment.
Okay, so where does the real math actually start? It starts with the grid's minimum energy requirement. For this specific project, the grid study demands exactly 20 megawatts of active power for a 45-minute discharge duration. Do the math, and that calculates out to 15 megawatt hours. But engineers can't just stop there. We have to factor in the real world. A 90% round-trip efficiency penalty, a 90% depth of discharge limit. Once you push that raw grid demand through all those real-world efficiency penalties and add a buffer for the battery degrading as it ages, you finally arrive at the true anchor of the project, a 20 megawatt-hour lithium iron phosphate, or LFP, battery capacity. And to supply that active power while also juggling reactive power for the grid at the exact same time, that takes some very serious hardware. The total apparent power required for this system hits approximately 43 megavolt amperes. So, to ensure a really healthy 3% design margin, that 20 megawatt-hour battery is paired with a massive 45 MVA bidirectional power conversion system and a matching step-up transformer. This is the heavy-duty equipment needed to instantly blast power back into the network the exact millisecond it is needed. Which brings us to section 3, engineering the cables. With those massive core components locked in, engineering the physical cables is literally about bridging two completely different electrical worlds. We're taking a 1500-volt direct current battery system and linking it to a 33 kilovolt AC coupled connection. And the engineering math required for each side? Totally different. On the DC side, engineers are obsessing over string lengths and how much current the cables can handle in the sweltering heat. But flip over to the low-voltage alternating current side, and suddenly it's all about how deep the cable is buried, grouping factors, and the thermal resistance of the dirt. When you distill all those massive engineering spreadsheets down, verifying the design really just comes down to simple pass or fail conditions. For example, our DC string cables pass with a microscopic voltage drop of just 0.021%. That is exceptionally efficient. Practically zero power is being lost as heat in those wires. Meanwhile, our 300mm aluminum AC cables are running at a hearty 170 amps, which puts their physical loading right at 91%. That safely handles the maximum continuous load, but sitting at 91% capacity means you are right in the sweet spot. You aren't wasting money over engineering with cables that are way too thick and expensive. And finally, section 4, the grid always wins. The grid impact study isn't just some minor footnote in utility scale design, it is the ultimate authority. For this site, the utility looked at their 33 kilovolt network and realized they required 38 megavolt amperes of reactive power just to keep their voltage stable, along with 20 megawatts for peak shaving. Boom. That analysis alone entirely dictated the 45 MVA conversion system and the 20 megawatt hour battery we chose. The local EV charging needs, the construction power, they just get to go along for the ride. The broader electrical grid dictates the final layout, period.